This is Precalculus Concept 22A. We're going to be looking at some models of exponential growth and decay, starting with exponential growth. These turn out to be some pretty meaty word problems, and the big difference here is that you're going to be expected to come up with the formula rather than being given a formula, based on the information and the fact that it's going to be either exponential growth or exponential decay. The good news is the formula is going to have the same format for all these problems. And it looks like the following expression. If I want to find the amount of something, whether it's money or people or bacteria or whatever it might be, I can find it by taking the formula A equals A sub 0 e to the kt. This is exponential. Hopefully you recognize that. Our base is e, and so we're going to be consistent and use e for all of these problems. And really, what the problem boils down to, before you even can use the formula, you have to figure out the values of a sub 0 and the value of k. And once I have those two things, I have my model, and you can proceed to solve the problem. So, a couple things. The a sub 0 stands for something. It's going to be the original amount of whatever it is that you are talking about. And then k is going to be something that you have to figure out, and it represents the growth rate. Okay, so it turns out a sub 0 is very easy to find, and k requires quite a bit of work. And we're going to start out with problems where the k ends up being positive, and that simply means exponential growth, which would be the graph here down on the left. The second lesson today will be exponential decay, which is the exact opposite if k ends up being negative. Alright, let's jump in with an example here. We're going to try to come up with an exponential growth model for the population of the United States. If you read through this problem, you will see that they asked for both the model and then an additional piece of information in Part B. So right off the bat, I want to start with my formula. A equals A sub 0 e to the kt. And then my job again is to figure out the a sub 0 value and the k value. Reading through the problem, I'm given two different populations, one in 1970 and one in 2007. And the good news here is you can choose whatever you want to be your initial, in this case, population. And hopefully it's pretty obvious that choosing the population 1970 would be a good initial population. So we're going to actually use t equals 0 because that's kind of our reference point, and that actually makes the a sub 0 that 2003.3 number. We also want to keep in mind that everything else in the problem is based on 1970, right? So the other piece of information there is really the 37th year. I'm getting 37 by taking 207 minus 1970, right? And so the population in that year was 300.9. So we're going to use those two pieces of information to find those values in my model. And again, the good news is that that initial value, right, is whatever I choose it to be. So I've defined 203.3 to be my initial, in this case, population. And so I've found that value. And the second half of this problem is then figuring out k. So as you might imagine, I'm going to use the second value there. The t value is 37. The amount of people is 300.9. So 300.9 becomes my answer. 203.3 is again my a sub 0. And my time is 37, so my exponent now is 37k. And whatever the solution is to this exponential expression is going to be my value of k, and once I find k, I have my model. All right, this should look kind of familiar. We've done a few of these problems lately. We want to solve for k, but before I can do that, I've got to isolate my exponent. So I'm going to take the 300.9, divide by 203.3, and that gives me e to the 37k. And from our last couple lessons, hopefully you remember that natural log of both sides is going to be a really nice way to simplify this. On the right side especially, that whole expression cancels and just gives me 37k. and I have no more exponent, and I'm actually one step away from solving for k. So my k value is going to be the natural log of 300.9 divided by 203.3 all over 37. And when you punch this into your calculator, you're going to get a pretty long and messy decimal. As a rule, you want to keep 3 significant figures. So significant figures are going to be basically the number of digits you'd keep after the first digit you encounter, your first non-zero digit. So this one has a long chain behind it, but if I look at just the first 3 significant figures, it's 0.0106, right? So even though that's 4 digits total, it's 3 significant figures, and so I want to use that as my k. So all that work leads to our model. Right? So our model is the population at any time is going to be my initial population, which we determined was 203.3, times e to the k, which is again 0.0106 t. And the model is really powerful now because I can figure out the population at any time, or I can figure out the time for any given population. So we're not quite done yet. We've done part A. Part B is to figure out the time at which the population reaches 315 million. And you're going to see that this becomes a really similar problem. I'm going to do part B in green here. So I'm going to plug in 315 for my answer and 203.3 as my initial condition. I have the same stuff over here on the right. And now, instead of solving for k, which I've already done, I'm solving for t. So I'm going to take 315, divide that by 203.3, and that's going to equal e to the 0.0106 t. I'm going to log both sides, natural log both sides. That's going to give me just the 0.0106 t part of my exponent, and so my final time in this question is going to be the natural log of 315 divided by 203.3, and then that quantity over 0.0106, and the approximate year for that is 41 years. Approximate t value is 41 years. Here's why I want to remember that my base year was 1970. So if I take 1970 and I add 41 years, I get 2011. So 2011 is the final answer to part B. So a lot of parts to this problem. You can see where it might be easy to get lost, but your job is to maybe watch this a second time if needed to, but you should be able to apply this technique to any kind of exponential growth problems. The most common ones are populations and problems involving money. Both of those are good examples of exponential growth. Alright, so next box is a you try. This is actually box 3. Sorry about that. And your job is to read this problem, see if you can come up with the model for it, and then answer the question. Sorry about that. And I'll let you go to it. One hint is that your formula, even though it's a different problem, is still going to be the same formula. Your job initially is to figure out a sub 0, right, whatever that is, and k, and once you have that, answer the question, which is, in what year will the population of Israel be 9 million? Alright, if you got the correct answer, congrats. This is not an easy problem, but again, the more you see of these, the steps are the same every time. So, starting off with my general equation, that's up here, the hint that I gave you. And right off the bat, I have my initial population, which is basically the first one given to me in the year 2000. So I can start off with the a sub 0 plugged in. The next thing is to plug in the second example, which is 50 years later. The population is 10, so I have a time of 50. and a population of 10, and then solve that through the process that we've talked about, isolating your exponent, natural logging both sides of the equation, and coming up with a value for k. And that leads to my model. So my model's here in green, and I can use the model to answer the question, which is when does the population reach a 9 million mark? And you can see the work is very, very similar, except this time I'm plugging in 9 for A and solving for T, but the steps are almost identical. So you're going to isolate your exponent, natural log both sides, and solve for T. The answer you get is 39. Remember that that's 39 years since what you decided was your initial population, so that's the 2000 year. And so 2039 is the final answer.